my life so far has been a dream since that launch. Like, I don't want to wake up from this good dream.
Boy, am I excited to share this conversation with you today. I've been working on getting this interview for the past several weeks. In fact, if you can see in this message, I sent this message to Jeff Cheezum on December 14th. So who's Jeff Cheezum, you might ask? He is a Northrop Grumman engineer. He was in charge of the design for the Sunshield for the James Webb Space Telescope. He's worked on the telescope for the past 14 years. It was such a treat to talk to him about what it's been like working on Webb for so many years, and then finally now to have it successfully deployed and on its way to Lagrange Point 2. He was just such a great interview, and I really think that you guys are going to enjoy this conversation. So let's go.
5, 4, 3, 2, 1, 0.
How are you feeling?
Oh, I feel great. I mean, I feel, super. couldn't be better, with how everything went. So very, very happy that everything went really well. Kind of validates everything we did over the last, 25 years from a program standpoint. And
right.
My last 14 years. So, it's been my life for the last 14 years. So it's actually know that it's up there and performing well so far. So
is it almost like, I know some people get like, post whatever event blues, like, is it almost sad that like?
Yeah, it's both, because, I've been, especially over the last like 4 or 5 years, when we've had the hardware on the floor, like behind me here, it's like almost part of the family, right? It's your child. You go out there and you work with it every day, and you take care of it, and you make sure things are going well with it. And then, once you launch on that rocket, it's gone. Now, yeah, it's sad not to really see it anymore, But I'm just so happy that it's out there. It's such a mix of emotions, It's hard to characterize for sure. But I graduated from college in 2001. So I worked for another company in Florida on space deployable reflectors to about 2007. And then, I moved out to California and started working Northrop, and right away started working James Webb, because we were, right in the beginning stages of our Sunshield design. And, the only thing we pretty much knew at the time was, well, we want it to be this big and this number of layers and this type of coating, but how do you actually build it and put it together and test it and fold it and stow it, and what are all the different extra features you need to be able to do that on the ground and ensure success. So, there was a lot of development that had to happen over the years to make sure that it did perform the way it did. That was my first job at Northrop, and luckily been able to stick with it ever since. So I wanted to stay with it. I'm a big NASA buff. I'm a big space nerd, Star Trek nerd, all that stuff, So working on a NASA program was a dream of mine. I had actually interned on the space shuttle back in '98 when I was in college, and that was very inspiring for me. I knew that I wanted to work on some type of NASA project, and so when the opportunity was there to work on Webb, I couldn't believe it. And I had some background in soft structure deployments, so it kind of fit right into my wheelhouse, kind of that next level step. I was used to small mesh reflectors that, was kind of just this one material. And now we're talking, hey, we've got 5 layers that we have to fold up into this tiny space and try to deploy it autonomously on orbit and not have it snag or hang up or anything like that. And so the challenge was there, and I love a challenge. And it was, it was great. It was a great fit. I just can't believe, like you had said before, 14 years is, it's kind of a blur, but I kind of remember it all too. It's this weird mix of how I can't believe that we're already here. But I remember during the time, thinking, are we ever going to get there? It seemed so far away. Everything we had to do, every step we had to go through, every test we had to do, it was just like, man, is that time going to come where we actually package this thing up and send it on a rocket? So having that happen this last month has been like a dream come true.
Probably doesn't even feel real in some ways.
It doesn't. I was just thinking about that, like literally like an hour ago. I was thinking, man, seeing that rocket launch from Kourou and just being there with it, getting hoisted up onto the rocket and working with it in its last moments and watching the fairing come over it and knowing that it was getting encapsulated and that was it. That was the last time humans were going to see it on the Earth. I mean, it's giving me chills right now. And I'm just talking about it. It's like giving me chills. And it was an amazing experience. I could not believe it. It does feel like since that launch, my life so far has been a dream since that launch. Like, I don't want to wake up from this good dream. Launch was so successful. All the deployments were so successful. Things are going really well. And I just want this to keep going, until we get that science data 5-6 months from now. I can't wait. I am definitely resting easier. I feel great, but I still got that, we still got that 5 to 6 month period where, we've got to get all the temperatures down. We've got to get all the mirrors aligned. We've got to get to the L2 orbit and make sure we're in that correct halo orbit and everything's going right. So there's still a lot that I don't have really control over now because I was mainly a Sunshield, design engineer and the mechanics of the deployments and everything. But I still feel, as a Webb, team member, we're all one big team, and we all still feel like, hey, we want this to be super successful, and I won't rest completely 100% easy until we get that data.
Wow.
Pictures.
And yeah, I mean, Christmas Eve, like, did you even sleep?
Nope, I did not. I had a hard time sleeping that night. I was so excited. And it was all right because I had to get up like at 5 a.m, so we could get out to like the launch site and everything anyway. So I was like, I think I got maybe a couple hours, but I was in and out of sleep all night that night. So just super, super pumped, super excited. I knew it would go well. I knew things would go well. I just wanted to get there. I just wanted to see it go well. And so it was a whole bunch of excitement. Very hard time that night.
Tell me like what the atmosphere was like the day of the launch in French Guiana.
Yeah. A lot of excitement. I mean, I wish our whole Webb team could have been there. We had a select few of our people from Northrop and NASA, and it was really good to be with a lot of those people. Everybody was just super excited. We got to go out to this area called the Toucan site in French Guiana and in Kourou there, and I think it's like the closest you can be to the launch site, and so a limited number of people can be out there. And so we get out there, and typical Kourou weather, it's kind of misting a little bit and rainy, and the cloud covers over top and everything, but it didn't matter. You could feel like everybody's excitement and energy about this. Like, it felt like it could have been a beautiful sunny day just by everybody's attitudes and excitement. We were all out there, and you could see the rocket, and you could hear this kind of noise, this kind of booms every now and then. And, we were thinking, man, what is that? Some of us didn't know. And I guess it's when they're kind of topping off the fuel for the rocket. And so every time some of it kind of escapes, it sends out a sound, and just feeling that little bit of sound right before the launch was going on, I was like, man, this is real. I'm hearing the rocket, I can see it not far away, probably, I think it was like 3 miles away maybe. And it just felt, it felt incredible that was going to be real right there. And then that launch was just amazing. I wish it was a clear day because, we only got to see probably 5 to 10 seconds of it before it went up into the clouds. But I don't know, that launch was amazing. Even for me, who grew up in Florida. I grew up in Daytona and went to school in Melbourne in Florida. And so I saw launches a lot. I saw a lot of space shuttle launches, a lot of rocket launches. But to know that Webb was on there, and to know that I had been, working atop that rocket not too long ago, getting Webb ready for its flight, it just brought just so much speciality to that launch. Felt so connected to it.
Right.
So seeing it go was just, again, felt like a child going off to school or whatever, going off to its future. It's just happy, sad, everything all together. It was amazing.
Yeah, you're sending it on the bus that's not going to come home.
Right. Yep. Go out and do your job. So
I've done a couple interviews with Harvard astrophysicist and astronomer Jonathan McDowell about Webb. And, he said the thing that he was most nervous about was the Sunshield. And so maybe, would you agree that was kind of on the inside what people were most nervous about? And
yeah, I agree. The Sunshield was definitely, not just because I worked on it. I mean, it is a very complicated, piece of hardware. I mean, it's multiple pieces, and it's not just the Sunshield itself. People look at the Sunshield and say, oh, it's those 5 layers. You just pull it out and tension it up. But, there's a lot of mechanisms that have to release and deploy, because if they don't, that Sunshield's not coming out. And then without that Sunshield, the telescope is just blind. It's not going to be able to see what it needs to see in the infrared. So, yes, from a mechanical standpoint, you have what they call indeterministic hardware. The Sunshields themselves, they're not just hinges that can open up from point A to point B and latch out, that are very deterministic, that it's going to happen. These are, it's like everybody knows how hard it is to make your own bed, right? I mean, just take the sheets and try to get them around there and everything. It's a pain. Imagine a tennis court size, bed with 5 sheets. You got to get in there all perfectly pulled out, and you've got all these release devices through it and all these cables. We have like 90 cables that are pulling this thing out, and can't get tangled up. They can't get caught around anything. And you're not just doing it in 1G where you can control everything. You're doing it in 0G where things are able to float around and go, wherever they're going to go. So we had to make sure from the point of completely stowed to completely deployed that we were controlling those membranes, the Sunshield layers and the cables as much as we could. Keep those cables in tension, keep the membrane somewhat taut and controlled, so that we weren't getting it billowing up into the telescope area or down below into the spacecraft bus area, where we have other deployables and hinges and mechanisms where things could get caught in and get stuck. So controlling that over that whole area, and during that couple hour deployment on each side, and then 2-day tensioning process, it was a very big challenge. So yeah, everybody was nervous, of course, about the Sunshield, I think most of all. But in my mind, again, like I said, I knew it would go right. Like I knew how much testing we had done on this. I knew how much we did. I know every bit and part of that Sunshield, and there was just no way it was not going to work. We put so much thought in it and done so much. And so it was kind of one of those things, like if it wasn't going to work, it was going to be an unknown. It was going to be something we hadn't thought of, or just some unknown issue. But, all the knowns, could this go wrong? Could this happen? Could this cable get caught around this? Could the membrane snag here? Could this release device not pull out? We tested every single one of those scenarios. And so in my heart, I knew it was going to happen. I was just relieved to see it actually happen on those couple of days that we were doing that.
Yeah. Tell me about like the testing. Was it, did you ever do was it in little bits, or did you do like the whole thing as a dress rehearsal? Like how did you test that?
Yeah, testing began, when I started back in 2007. I mean, we had to figure out how to hold the Sunshield in place and not have it move around too much on launch, or make sure it could vent properly and make sure it didn't just blow out because of trapped air and get damaged that way. So one of the first things I did when I started was actually testing how to reinforce the membrane so that we could actually put release devices through it. Because when we fold it up, we've actually got to put a release device through it at these 107 locations in order to hold it throughout its whole structure from the back end all the way to the forward and onto the spacecraft. So just developing one, that it seems like such an insignificant thing now, but if that reinforcement hadn't been tested properly and built properly and installed properly, then that release device might not have held the membranes in place for launch, or it could have torn while it was deploying. So things that could have damaged it. So a lot of testing was done by making a lot of samples and different designs and testing their strength and what we call instron machines, like pulling the material and making sure that we're gonna hold to the loads that we're putting into it. And then from there we kind of build up. We go to subscale articles. So we would build little sections of the Sunshield membrane. So the section that goes over top of the spacecraft bus. When we fold up Webb, we have those two large pallets, the forward and the aft pallets, and between that and the spacecraft bus, we have other structure that kind of folds up in kind of a V formation, and so our Sunshields have to actually, come down from the top of the structure all the way down, go into this V formation, and then go onto the bus. So we had to know how to fold up the Sunshield to make sure it wasn't going to tear, that we had enough slack in it to be able to have it, go kind of where it wants to go within these folds, and to hold it down in place. And so a lot of testing was trying to figure out how much slack do we need in the membranes, but not too much slack, because we don't want it to billow up and again hit some of the mechanisms or electronics on the telescope or on the spacecraft bus, because we were kind of boxed into a very small area. We had telescope above us and the bus below us, and we had the most number of folds on the sides of the membranes there that we had to fold up and get underneath there and make sure everything fit and didn't contact the other structures to where the membranes could get damaged. So a lot of testing on those subscale articles to make sure we could fold it up correctly, and that it would deploy out correctly without any damage. And then from the subscale articles, we go on to full scale articles. One of the smartest things we did for the program was we built full size 5 layers of the Sunshield. So the 5 layers on flight are actually numbers 6 through 10 that we built. We actually have, the first 5 layers that we built, we call them the template membranes. And they were our test bed to basically work out all of the manufacturing process, how to put in all the features that we needed to put in. And then actually, once we got them at our facility, we were able to do all of our testing as far as stowing them, folding them, deployments, making sure that, we had to develop all that. We had to develop, how do we actually fold it? What kind of ground support equipment did we need to be able to handle these membranes? You can't just have a whole bunch of guys picking it up and trying to, fold it into the spacecraft. You've got to develop this whole structure to be able to do that. So over the course of years, we built those template membranes. We worked with our supplier, who built them, Nexolve. They built them in Huntsville, Alabama. So I was traveling out to Huntsville for years during the build of those template membranes, and then finally for the flight ones too, to support those, and then bringing them here to California to be able to test them before the flight ones. So those were invaluable. We couldn't have done everything we did and really develop it. You can only do so much on a computer, in 3D modeling. You with the Sunshield membranes, that was not going to cut it. We had to have real hardware to be able to physically touch and do things with and test and figure out, oh, this isn't going to work or this will work, things like that. So very invaluable to have those template membranes.
Tell me how clean Webb, the whole workspace around Webb had to be.
Yeah, Webb has to be very, very clean. I mean, it's one of the highest classification clean rooms that we've got at Northrop. Any kind of, particulate, we as humans are the most, shed the most contamination, our skin particles, oils from our hands, little pieces of hair. So we got to make sure none of that gets on the optics, because as you can see behind me, right, all those optics are just sitting there waiting for something to get on it. So anytime we were working with the hardware, we had to be completely bunny suited up, what we call bunny suit, because I don't know, we don't really look like bunnies, but we're in these big white suits, and we've got the booties on and the gloves, and we're all taped up, around the hands and the face mask. And so you basically only see our eyes. So you really got to know people's eyes out there. You knew who people were when you were out in the clean room, just by the looks in their eyes. But yeah, we had to keep it very clean. We had a whole engineering section of what's called contamination control engineers, who just did an amazing job to make sure that, every part of the, not just the telescope, but the high bay that we're in. It's a very large room. We have these huge HEPA filters that are in the wall that are bringing in all the air, but we also set up all these sensors all around the high bay, all these sample collecting dishes to be able to tell how many particles are in the air floating around. They have what's called particle counters, which basically is like a little funnel piece that, take in air samples every now and then. And so anytime, particles were getting too high, we actually had times where there's, if too many people were in the clean room at one time, you'd have some particle counters going off saying, hey, there's too many clothing particles here going around. So, or whatever was going around just from all the people. So we had to limit the number of people around the telescope. But just, they were out there constantly cleaning too. They had people out there, always mopping the floors, cleaning all the hardware, any of the lifts that we had to use to go up on. We always had to use lifts because, we're 3 stories high, we've got to go all the way to the top. We've got to get over top of everything. So, we've got to clean all those lifts, because sometimes lifts can, shed paint or a little bit of oil or something if they've got, hydraulics and stuff in them. So every little thing that's moving, that's going over top of the observatory had to be clean. We had to wipe the bottoms of our booties every time we went over top to make sure we didn't drop, get anything from the floor dropping from our booties on top. We implemented sweat bands, because sweat itself, when you have people working over top, you're in a bunny suit, right? So you're getting kind of warm, especially if you're moving and working around. So early on, we actually had issues where we discovered, hey, what are these little spots on our test membranes here? We noticed that sweat would actually eat the vapor deposited aluminum, that silver color that you see on the Kapton. It would actually eat through that coating. And so you just see the bare yellow Kapton material. And we traced it back to, well, it's sweat. People were, dripping down sweat from their head. So implement, sweat bands. So everybody had to wear sweat bands on their heads to make sure. And the protocol was, hey, if you feel like you're getting warm or hot or sweating a little too much, you got to get down, you got to get cooled off, get out of your bunny suit, wipe yourself down, cool off, drink some water, get back in there, and then get back working. So, just those little things, everyday things that you don't really think about. We had to make sure we were doing to keep Webb clean. So a lot of protocol was in place to make sure that we were clean.
So, and it was built in El Segundo, right? You're in El Segundo?
Yeah, Redondo Beach is actually, it's weird. El Segundo, Redondo Beach, it's all kind of a mix at Space Park, but our Space Park facility where we built this, the address actually in Redondo Beach.
In Redondo, okay. This may be a dumb question, but how was it transported to French Guiana?
Yeah, no, not a dumb question at all. People, that's a great question, because, it's pretty far away, right? It's another continent. It's
and we want to keep it clean.
and we want to keep it clean. Yeah, exactly. So NASA actually had a shipping container called OSTARS. It stands for shipping of transportation of air, sea, some kind of acronym like that. But you can look it up, OSTARS, and it's this big clean room in itself almost. And so we had to actually take Webb, we had to fold it all up to its stowed condition, and then this was one of the most exciting and crazy things I've ever seen too. Is we take Webb from vertical and we put it on a rotation fixture, and it rotates it down to horizontal. And it's the first time I've ever seen like our whole spacecraft be in that position. So the mirrors are facing down, and yeah, the whole thing. And you're just like, oh, am I going to hear like something fall out or something? I'm going to see something drop on the ground or whatever. And luckily, none of that happened. It all held together great. But yeah, we've got to do that to be able to transport it. And then we pick it up off of that fixture, and we crane it over into the shipping container. And then the shipping container has a top that goes over top, like an inner liner top that goes over it, and it completely closes it out. It's all nice and clean. It's all encapsulated. There's purge air going in there to make sure we've got clean air running through around the whole telescope. And then we put on a second top on top of that to kind of seal it up, just to keep all the elements out from outside. So it's completely protected in that shipping container. And then we actually transported that whole shipping container from our facility in Redondo Beach and took it down the 405 for a little bit, and then took it down some surface streets all the way down to Seal Beach, where there was a ship out there from that Ariane Space uses to ship all of their stuff, like from Europe to South America, like their rocket components. Mm-hmm. It's called the MN Calibri. And so it was there waiting for us. And we basically, pulled it up on there using a tractor trailer, put it on that ship. And then that ship took I think it was about 2 weeks or so to go from Seal Beach down through the Panama Canal and then to the launch site in Peru. Oh my God. It's taking it out of that ship and driving it to the facilities in Peru.
Were you there before it got there, or were you there after it was already there?
I was there after it was already there. So we kind of, we got there. I think the vehicle got there in early October-ish timeframe. So there's a good 3 months of work that we had to do and support. And so we had guys from Northrop out there actually supporting the whole time. That was incredible work for them to do for 3 months. I can imagine being hard, being away from family and everybody for that long time. But we were able to split up our engineering team a little bit, which was good. So my shift, as you could say, was the last part of the trip. So the December timeframe. So I got out there December 3rd, and I was out there till the launch.
Oh my gosh.
Yeah, so it was still good amount of time, about 3.5 weeks or so, 4 weeks maybe. So still a good amount of time. But it was cool being there for that time. Before that, there was a whole bunch of inspections and that we had to do. One, getting it there to the facility and then bringing it from that horizontal position to vertical. So the engineering team that was there had to do those inspections and make sure, hey, did it survive the trip, across the ocean and through all those the roads and everything, and make sure everything looks good. And luckily everything looked great. Everything was where it should be, which is a good thing. And then it went through a fueling process. So our spacecraft actually gets, put fueled on board. So we have a team that has to, dress up in these big hazmat suits and everything and go in and fuel it up and make sure all that's correct and that we've topped it up as much as we can with the fuel. And as we're doing these stages, it moves from building to building in Crew. There's a couple different buildings. So when I got there, we'd just been fueled up and we were in kind of our last staging area, getting ready to go over to what they call the BAF, the BAF, or it's their final assembly building where the rocket actually goes into, and that's where we picked up Webb and put it on top of the rocket and closed it in the fairing. So large, huge, very tall building for their Ariane 5 rocket. So I felt like I was very lucky to be kind of there at that stage, because I got to, do the final inspections. One, when we moved from the fueling building over to the BAF area, do those final inspections, and then as we lifted it from the floor up on top of the rocket, doing those kind of final inspections, just making sure everything was in its proper place and ready to go, and supporting Ariane with whatever operations they needed to do to get the final, hookups correct, and then the encapsulation of the fairing, and then watching in the rollout to the pad, and then finally the launch and all that. So
there's
great 3 weeks.
so many steps and so many decades of hard work and so many things that could have gone wrong. I mean, talk to me a little bit about, that clamp malfunction. And, I know that there was some coverage about that, but did that kind of shake your confidence at all when that happened?
It's always kind of nerve-wracking when something doesn't go according to plan. But I had confidence in Ariane and them, handling our hardware. They've done so many, so successful with the Ariane 5 and that team. When I was there working with them, I mean, those guys were great. I mean, it was so cool to see them work and see how they handle everything and how they operate. So, it wasn't an unfortunate thing that they did have the clamp band anomaly when they did. It was definitely something we didn't need at the time, but like I said, we have confidence in them. We knew that going forward, things would go well. We were able to get a lot of data from like stuff we had on board and everything, and really examine the hardware and make sure everything looked correctly, and use data from past events to be able to make sure that event didn't happen, didn't cause any damage on JWEST. So that was good to be able to be a part of and work on and make sure we didn't have any issues. So I mean, short answer is yes, of course. You don't want that stuff to happen. You don't want little things like that. And it's one of those unexpected things, right? You don't think that something that gets done multiple times would have the issue, but sometimes it's those small things that you're looking at the big complicated things that can go wrong. And sometimes maybe somebody misses something on the easy end that, hey, we've done this 100 times, it's what could go wrong, right? It just shows you that in the engineering world, we've got to look at every little thing, no matter how small you think it is, or how many times we've done it, or how routine it is. It's just not routine with engineering. You've got to, if you're not careful and you're not following that procedure exactly right, and you're not having those double checks and making sure everything is perfect, you're going to miss something. You cannot sit back and just say, it'll be fine. We've done it before. I know this is going to work. So I'm not saying that that's what happened or anything. It's one of those things you just gotta make sure you're thinking about every little thing, even the small stuff.
Yeah. No complacency.
No, not at all. For sure.
I read an article saying that like James Webb was originally supposed to launch in 2007 or something. So can you talk to me just about like the delays over the years and you working on the inside, what that was like?
Yeah. I mean, I think a lot of it was, initially when companies bid for stuff, they're gonna say, you can't always realistically, unfortunately say it's going to take 25 years to build this machine at $10 billion. You would never get the contract, right? And not that anybody knew at the time that would be the case. So it's just one of those things that, it's for a first time build. Things are going to be way more complicated than you can probably ever imagine. So the delays, I think, were inevitable. But yeah, over the years when I was there, I started in 2007. I think at that time, our launch date was around 2014 or so. So, there was just the complexity of Webb was just, more than people could have imagined, I think, back in the beginning time. So going through and trying to, like I said, when we had first started the Sunshield stuff, we didn't initially think we were going to build template layers to be able to test the Sunshield out. But we realized early on that, hey, we're not going to be able to really figure out how to fold and stow this successfully to be able to do this on flight unless we've got full-size layers here to be able to test out. So, all those test articles that we had to come with, that's just one example. There's many, many other test articles that weren't in the original plan that had to get put in there, because our main goal was, it's not schedule, it's success, right? It's success technically of the program. And so unfortunately, schedule is going to slip for that. And with such an important project like Webb, for the astronomy community and for science and for humanity as a whole, we were not going to send up this thing or complete it until we were sure that everything was going to be right with this vehicle. So, the delays had to happen. And as I think we would have probably not had a successful mission if we would have pushed faster than we did, or skimped on test articles, or didn't do, all the analysis we needed to do and everything like that. We had to do everything that we did in that time period.
Right.
Be able to ensure the success we've got now. I mean, it's not good for morale a lot of time when you're on the program and things keep slipping and slipping and slipping. And you're like, and from the public, right? Everybody's like, hey, when are you guys going to get Webb going on? What's going on here? I've seen tons of hilarious memes over the years of skeletons waiting in their office, like, when is Webb coming? Come on, I've been waiting here for years. I know, trust me, I wanted to get it up as soon as we could too, though that was not a desire to have it as long as it was. But again, I'm glad we did everything we did, because if we hadn't, we wouldn't be in the successful state that we're at now. So, well,
I mean, there's, you obviously don't want to rush it either, because it's not serviceable. So
exactly,
it's not like Hubble. It's going way, way, way further away.
Yeah.
So
yeah.
Let's
Well, Hubble's only a couple 100 miles away. So it's, easy to get to, right? So we're going 1 million miles away, and, 4 times the distance to the moon's orbit. So I have confidence that in the future, we'll be sending humans out, to that point, or, to Mars one day and everything, and we will get there. But yeah, in the near term, we're not there yet. So it had to work on its way out there and out there 1 million miles away. So that was a huge factor in us making sure that this thing was going to go right. Definitely.
So with this kind of, pioneer origami style deployment, like, are we going to see a lot more of this in the future, do you think?
I think it's a possibility for sure. I mean, to build, this is the largest deployable that NASA has made as one unit going up and being able to, transform, right? It's a big transformer almost, and become what it is behind me out there. And it's not even fully deployed out there, right? You got the mirrors segment still folded up there. But, of course, the International Space Station is huge, right? But it got sent up in chunks that could fit on the space shuttle or whatever.
Right.
And put together again in a low Earth orbit where we could get to. But yeah, to be able to build larger spacecraft, if we're gonna keep doing things, trying to get the whole enchilada on a rocket at one point, you've got to be able to fold things up like this, or have them become assembled in orbit autonomously, far away without human intervention until we can figure out how to get humans out there quicker. But yeah, I mean, I think it's definitely a future, a way to go for future spacecraft. I mean, you've probably seen the next kind of iteration that NASA's thinking is called LUVOIR. It's ultraviolet telescope, and I think they kind of took the Webb model and scaled it all up and maybe instead of a tennis court, we're going to have a football field, the Sunshield, and we're going to have a mirror that's 3 times as big, and I think it's a possibility. But I'll tell you what, you see how Webb went, right? 25 years of work and development, and yeah, we've got kind of now a lot of the basics down, but this stuff just doesn't scale up perfectly. Like, oh, I can just make it twice as big or 3 times as big, and it's going to be no problem. It's not gonna work that way. There's still going to be a lot of first time developments about maybe a better way to fold the Sunshield if it's bigger the way it is, or the structure itself, just handling the structure on the ground. I mean, we put to be able to counterbalance our telescope, because our telescope lifts up, or the optics, the mirrors and the instruments back there lift up 4 feet up in the air. And so we had to build this huge counterbalance weight system that's attached to the beams. They actually had to redo the structural beams up at the top in the clean room to be able to put in this big counterbalance crane system so we could lift up, the optics portion, so we could do our testing out in our clean room. And so if you're talking about doubling or tripling the size of that, I mean, you're going to need such, immense ground support equipment and facilities on the ground to be able to test those. So, but yeah, folding things up, I think as long as we're doing that, we're coming up with bigger rockets though too, which is good. So maybe, once I know you're a big SpaceX fan, and the Starship and everything is a huge rocket. So I'm sure we'll be able to put a lot of huge spacecraft on there where we don't have to fold up as much. You can lock things out in place already and have it ready to go. I don't know about a Sunshield. That would be interesting to me, if you could a Sunshield. Oh, sorry about that. And it's sorry, and it's full state. I don't know about that, because the vibrations and everything like that. You've got to have things locked down on a rocket. So that's the other important thing, is you can't have things just kind of out there flimsied or tensioned the way the Sunshields are. You'd have to have things locked down and then deploy it.
Yeah, so even if they had the room, there's still benefits to stowing it properly.
Yeah, just for that vibration and acoustics of the launch, for sure. So, it'd be great if, like I said, I'm a big Star Trek nerd, so I think of things that are just probably physically impossible and not able to do right now. But if we could get away from rockets somehow and somehow get things from here to on orbit without, that vibration and that acoustics noise, then you just take stuff up, smoothly and
right
together and don't worry about it. So I know one day that can happen. I just don't know if it'll be in our lifetime.
So I feel like there's been pretty good media coverage of James Webb, but for the people who live under a rock or are not really big in the space community, what would you tell them to get them excited, and why this is just such a big moment for history and humanity?
Yeah. I mean, so Webb's, it's got 4 kind of main missions, to study the birth of stars, study how galaxies are formed, study exoplanets that are out there. And because it's an infrared telescope, it can look, as it's looking further out, it's also looking further back in time, because it takes so much time for that light to reach the telescope or reach our eyes. So it can essentially see, the early universe as it was. And we don't know what that was like. There's, to me, it's fundamental questions, right? Of existence, of why we're here, of how things happen. We're not gonna understand it unless we look into space and see how things were formed in the beginning, and see examples on other planets in order to understand us and our own planet. The thing I'm most excited about is the exoplanet study. So awesome that in the last 10 years or so, or how many ever years, we've been discovering these exoplanets around other stars, and Webb has instruments on board to be able to actually detect what type of elements might be in those planets. So to know that, hey, we see another exoplanet with oxygen or methane or carbon dioxide, things that we know are indicative of life, that to me is going to be the most exciting thing. I mean, to know that there's a larger community out there of life, in the cosmos is just going to be an amazing discovery. I hope that Webb is the first to be able to find that out for sure.
How excited are you to get back those first images, 5 or so months from now?
Yeah, very, very excited. I mean, again, I don't think I'll rest completely 100% easy until we get some of those images and they are looking beautiful, like the Hubble images look, so beautiful, but in the infrared spectrum. So we get different take on it that we can't see with our eyes. And it's going to be incredible. I'm going to be so happy when that happens, to know that everything we did, again, over the last 25 years or so has come to fruition. So very excited for that. Again, that'll be another point where I'm like, is this real? Is this really happening? I'm kind of at that point now with the launch and the successful deployments of everything. But that next big thing for me is definitely getting those pictures and seeing what it's going to see and learning, maybe coming up with more questions about, man, what was this? We had no idea what things would look like this, so can't wait to see that for sure.
What was the hardest challenge for you personally as you were designing the Sunshield?
Oh boy, that is a great question. So many challenges about just the sheer complexity of trying to make sure it would fold up correctly and deploy and not get any tears. It's susceptible. It can be susceptible to tearing. It's a very thin membrane material. It's kind of like a Mylar balloon. You could just take a scissor or a knife, right, and just cut right through it, no problem, right? But it's really, really strong when you try to pull it. If you don't have a sharp edge, if you're just pulling it and tension it, really, really strong and durable. And you can fold it up and deploy it, and it is very robust and handles that. But only for so many times. You can only fold this thing up. It's kind of like if you took a piece of paper or something too, and you folded it and you just kept exercising it back and forth and back and forth. Eventually, you're going to start wearing it out. You're going to start getting some wear and tear in there. And so, same thing with the Kapton. So we had to be careful about the handling of the membranes. We wanted to test them as much as possible. It'd be great to fold and stow and deploy these things, as many times as we wanted. But there's only so many times before you start inducing some real permanent damage to these things. So, luckily, again, we had those, our 5 template layers that we built before these, and we were able to do a lot of that testing and kind of see how these things would handle it. But, we did see, tears start to happen on those, and we had to come up with ways of repairing the membranes and patching them and have that ready to go. And so developing that whole process and making sure that when we were folded up in this very small configuration and when we deployed that we would be able to fix any issues we had or just avoid them altogether. So that was probably one of the biggest challenges. And also, managing a lot of the cable that we had. Again, we've got 90 cables that are pulling these membranes at each of the 6 corners there. So we had to make sure we manage those. So just managing the cables during the deployment, making sure they weren't going to get looped around something or snagged around something. The membranes themselves, I designed some features to be able to keep the membrane in constant tension, so we weren't pulling the layers in one direction or the other. We always had that positive direction from where we were folded up to the end of the mid boom where it was pulling it out, so that not too much of the membrane could float up and contact the optics or get damaged. So figuring out how to control the membranes in a zero-G environment without doing any testing in zero-G, very, very difficult task. So a lot, and I'm just kind of scratching the surface. There's just so much stuff we've worked on over the years with deployment mechanisms and tensioning systems and things like that. But
So of the 5 layers, were 4 of those simply just backups, or do they all have a function and a purpose?
No, in fact, probably if you were to say if any was a backup, it'd probably just be maybe one of the layers. But even that, we kind of probably still had to have all 5 to really get to the temperature we need. Because one layer isn't enough to make that temperature difference. The main feature that's causing that temperature delta from the bottom of layer 1, which is around 200 degrees Fahrenheit or so, to the top of layer 5, which gets down to about minus 380 Fahrenheit. So you're talking almost a 600 degree Fahrenheit difference. But the main feature that does that is the space in between the layers, the lack of air, the vacuum of space. It's an insulator, right? So it's able to basically get all that heat and radiation radiated out all the sides of the layers. So the coatings on the layers on the bottom of layer 1 is able to basically shoot back all that heat from the sun and the earth and the moon, the majority of it, but a lot of it's still going to kind of escape to the next layer. And so we've got to have those reflective surfaces in there to bounce out the heat out the sides, the 6 sides of the membranes. And in order to get that 600 degree delta, you've got to have at least 4 layers. The five layers you'll definitely get there. So not really too much backup there. They had to be that number of layers and that, distance of separation there and those coatings to be able to work the way we needed it to work.
So now that the, massively complex deployment is completed, what are some other, things that you're watching out for? Are you concerned about like micrometeorites, or, is it pretty smooth sailing from here with it? Yeah.
I mean, it is, as far as external things like micrometeorites, it's always something that we've, we knew of and we designed for. They are rare going where we're going to L2 orbit. We're not going through like an asteroid belt or anything like that. So, and, we're away from the Earth, so we don't have to worry about space debris of satellites or anything like that. So we're in a pretty actually good, clean area. So yeah, if you're not going to have large meteorites or just what they call micrometeorites. So very, very, very tiny, which could still at a good velocity, cause some damage because the mirrors are exposed, the sunshield's exposed. But luckily it's such a huge mirror, one little damaged piece or a couple of little damaged areas wouldn't really change the overall, capability of the mirrors to be able to see what they need to see. And sunshield wise, the 5 layers helps in that respect too, because, more than likely you won't get a micrometeorite going through all 5 layers. Maybe it goes through 1 or 2. But we designed in some really cool features into the layers themselves called rip stops. So we actually seamed in, these reinforcements, if you will, throughout the layers so that if we did get a micrometeorite hit in one section, we just don't get this tear that goes through the entire layer and rips the whole sunshield apart. It can only go so far to these ripstop areas and then it's going to stop. So something we tested and developed and, thought about because we didn't want one little piece to take out half a sunshield or whatever. So I'm not too worried about those. We'll get some, we'll be able to tell, I guess, from a lot of our temperature sensors, if we're getting heat signatures on the optics that are a little, not expected and maybe in an area, and then maybe we'll know if something's, going on with the sunshield there, but I don't expect any of that to happen. I think we're going to be pretty good. We've got the alignments of the mirrors coming up. So internally, we've still got a lot of internal work that has to happen, has to go right. But, they've tested all that on ground. And again, it's a little more deterministic. We've got motors and mechanisms that we know how they move. We know how the optics work, tested it quite a bit on the ground. So fairly confident in all the mirror alignments that we're going to have. The instruments on board, we've got the 4 science instruments, the cameras and the spectrometers. Those have been in there for quite a long time, but they have been tested and purged and kept in a healthy state. So fairly confident those will be good. but there's a lot of electronics on board. We've got our solar array and our communications antenna and our batteries and our electronics and a lot of other things that have to keep going right and keep going that 10 or now I hear 20 years, which is cool for Webb, of life that we've got in us. So, but we've got backups for things. We've got reaction wheels right on board. That's a big deal for us to keep our station and make sure we're pointing in the right direction and things like that. But we've got backup reaction wheels. We've got A side and B sides of things, so we can have backups if something does fail in one of the electronics or something like that. So it's good that we've got redundancy on a lot of this, a lot of the hardware. So to me, I think our biggest challenges are definitely behind us, but for sure everything's got to keep working. And now that I hear that we did the Ariane guys did such a great job on their launch for us that looks like our life got extended from a 10-year life to about 20 years.
Wow.
Based off our fuel consumption, we could still do better than that if we don't consume a lot of fuel for station keeping and pointing and things like that around when we're in orbit. So, but hey, that's great news because I think we need to keep this thing going as long as we can.
Right. Any other like fun trivia or maybe a favorite moment that you want to share now that I've grilled you about hard things?
Oh man. Well, fun trivia. Yeah. For people who don't know, I mean, the Sunshield is equivalent to us having, if you had sunscreen on with an SPF of about 1 million, so you have a SPF usually about 50. Our sunshade provides the telescope with a SPF of about 1 million. So that's a pretty cool fun fact that I like to share. And the other one that's cool too is that, the mirrors are that gold color. It's because it's best for infrared, for capturing infrared light. And so that mirror, and sorry, my cat is interrupting.
I was like, is that my cat?
No, that's mine. He's telling me he's hungry, I guess. But that mirror, that gold, the material itself is actually beryllium. So it's like a gray material, and they polish it down to make that mirror surface. And then the gold coating is just a very, very thin layer, like atoms thick of gold. If you were to take all that gold that's on those mirrors and got the mass of it, it's about the mass of a golf ball. So it's not a lot of mass of gold on those mirrors, but it looks beautiful.
It does. Wow.
Those are a couple of fun facts, but
those are fun. Have you always been interested in space and in that field?
Yeah, definitely. I was my main inspiration was Star Trek. Star Trek: The Next Generation actually is my bread and butter. I love that show. I watch it to this day. Episode's on. I don't care when it's on. I'm going to watch it, even if I've seen the episode like 8 times. So, and that inspired me to definitely. I originally wanted to be an astronaut. I still would love to be an astronaut. I applied the last couple applications ago to be an astronaut, but I don't have all those credentials, unfortunately. But I'm still going to apply anyway for the heck of it. But yeah, I've always been interested in space, science. It's just been a passion of mine since I was a kid. So I'm truly honored to be working in this field and working on such a prestigious program too, so definitely.
Do they give you feedback about like your application to be an astronaut?
No, they don't. I wish they did. Nothing. You just hear about, oh, this is our new astronaut class. And you're like, okay, I guess I didn't get picked.
Okay, interesting. Again, a big thank you to Jeff and his higher ups who had to kind of approve this interview. And I'm so glad that I was able to share this great insight of what it was like. What a beautiful moment that must have been to see the launch and to have all of these hard years of work realized, and to see James Webb so far as a success. I know that we have a few months to go to finally see those first images come back to us, and then we'll truly know if it's a success, but everything is looking great so far, and the hard part is out of the way. And so this was just really, really cool to be able to talk to Jeff and have him share his experience. And I mean, my goodness, just congratulations to everyone who worked so hard on James Webb. We all can't wait to see what we learn from what it finds. If you guys enjoyed this video, please make sure to give it a like. Please make sure to subscribe to the channel. And hey, this was such a cool conversation that you're not gonna see anywhere else. So make sure to share this video with your friends and tell me in the comments what you're most excited about with the James Webb Space Telescope. As you heard Jeff mention, there are 4 different kind of missions for Webb. So I think that I'm most excited in learning more about the exoplanets, but I want to hear from you what you are most excited about. As always, leave a comment below. Thank you so much for the support. A big thank you to my Patreon supporters, especially the super Patreons. You guys are allowing me to do some really cool stuff this year, including an interview with Scott Manley. I also have one in the works with someone else who I'm sure pretty much all of you know. So I'll keep that one a little bit hush hush and keep you guys guessing for a little bit. But hey, why don't you guess in the comments as well?